Hi there, folks. Today we're looking at components of polynomial graphs. So we're going to start talking about the graphs of polynomial functions and the different things that we look for as we look at these graphs, as we look at these curves. And the first thing we're going to talk about is increasing and decreasing, all right? Increasing versus decreasing. Increasing is when y is going up. So when we talk about increasing and decreasing, we're talking about visually the y values. Is the function going up or down? All right. So if y increases as x increases, we call that increasing. All right. Decreasing is when y decreases as x increases. And notice they both say as x increase. That's just a fancy way of saying going left to right on the graph. If you think about it, for x to be increasing, the smallest x values start at the left of the graph and the biggest x values are at the right of the graph. So x increasing just means going left to right on the graph. All right. So another way to state this would just be to say, hey, as we go from left to right, if the function is going up, that's increasing. As we go from left to right, if the function is going down, that's decreasing. All right. And the idea of identifying increasing and decreasing visually is really easy. All right. The thing that students struggle with is we can easily identify increasing and decreasing on the graph, but labeling it is a different story. We label it in terms of its interval, all right? So visually, we see increasing and decreasing in terms of y going up or down, but we label it in terms of x, okay? We visually see it in terms of the function going up or down, but we label it in terms of left and right, okay? And you'll see that in a moment when we get to the graph. That's the thing that's tricky, is the labeling, all right? Because we label it kind of using a different component, using a different dimension of the graph than we use to identify it, okay? Talking about relative maximums and minimums. A relative maximum occurs when the function goes from increasing to decreasing. We talk about these in terms of turning points, and really this is a foundation. Some of this stuff we're talking about right now, this is some of the stuff that you're going to explore in calculus, all right? This is the foundation for some of those pieces. So increasing versus decreasing, really it's a change direction. Relative maximum, it changes direction, all right? It was going up, now it's going down, all right? So we get this kind of high spot, all right, on the graph. And then a relative minimum is the opposite of that. It's when we go from decreasing to increasing. The function was going down and now it's going up, so I got a low point on the graph. And the reason we refer to them as relative maximums and minimums is because they might not be the lowest value on the graph, okay? Yeah, so a relative maximum might not be the highest value, and the relative minimum might not be the overall lowest value, all right? But the relative maximum is higher than the points around it, okay? It's a high spot, not necessarily the highest point on the whole graph, but the highest spot around that area, okay? When you think about that idea of relative, like if you've ever met me, I'm not a real tall guy. I'm at like 5'7.5", all right? 5'8" if I'm really stretching my neck out, okay? So I'm not extremely tall, but if we were comparing me, if I went into a kindergarten class and we compared the heights of all the students and threw me into the mix, I'd be enormous. I'd be huge. I'd be really, really tall. I would be a relative maximum. Okay, so even though my height wouldn't be considered a maximum when you look at the entire population, I would be a relative maximum in that room because I would be the tallest, okay? I would be the tallest compared to what was around me, all right? That's the idea behind a relative maximum. And same thing with a relative minimum, okay? If I went to the same thing, taking my height, if I went and stood in a room with NBA players, I would look incredibly short because I would by far be the smallest person, the shortest person in there. I would be the relative minimum in that scenario, okay? Even though I'm not the shortest person on the planet, I'm not extremely short in terms of the overall population. In that room, I would be considered the absolute minimum, okay? Because I would be shorter, I would be the minimum compared to what's around me at the moment, okay? That's the idea of relative maximums and minimums, okay? So we just look for those turning points. Where do they go from increasing to decreasing or decreasing to increasing? And then the end behavior. This is a pretty tough one, but the end behavior is what happens on each end of the graph, okay? That's why we call it end behavior. If you think about how the graph behaves on each end, Well, that would be the end behavior, okay? And once again, this is one of those things that we identify the end behavior in terms of why, all right? We talk about it in terms of, okay, on one end, is it going up or down? On the other end, is it going up or down? Is it going to positive or negative infinity? But we check it and we talk about it in terms of x as well. So the end behavior is kind of defined here in terms of x, but we look at it and we finish labeling it in terms of y. And so, again, don't be alarmed here by this notation. It says the end behavior is what the graph does as it goes to as x approaches plus or minus infinity. Well, that's just a fancy way of saying left and right. When you think about it, negative infinity just means, hey, that's as far left as you can go. All right. So as the function goes to the far left, what does it do? And positive infinity, well, that's just going right forever. And as the function goes to the far right, as it goes to the right forever, what does the function do? Does it go up or down? Okay? And so let's look at a graph here and let's identify some of these things. So increasing and decreasing, all right? Increasing is when the function is going up and decreasing when it's going down. And again, that's as x increases, so that's as we go left to right. So as we go left to right, if I were to kind of trace this function, let me trace it in purple. As I go left to right on this function, here's the path that I follow. See, look, I'm going up, so I must be increasing. Then all of a sudden it changes. Now I'm going down. Let me change colors, so now I'm decreasing. And now I'm going up again. And so as I follow this function left to right, I'm increasing. And it's really easy to identify. I can circle on the graph, say, hey, increasing, increasing. Those are the spots where it's going up as I go left to right, okay? And then in the middle here, decreasing. Really easy visually to identify increasing and decreasing, okay? But now here's the thing. We identify it in terms of the y values, in terms of the dimension of us going up or down, but we're going to label it in terms of x. I want to know the interval on which this thing is increasing. And so if I looked at that first purple section, the up and down tells me that it's increasing, but I want to label where it's increasing, okay? And if I want to label where it's increasing, well, I think about it and I say, okay, well, it was increasing until I got to this point right here, and then it was increasing to the left, right? So everything to the left, on the left side of this graph is increasing. And so when you think about that in terms of an interval, where did it start increasing? Because again, I went left to right on this thing. Well, if I think about where it started increasing over here in this section, I have to keep going to the left forever, right? So if I go to the left forever, that's where it started increasing. It increased from negative infinity until I got to an x value of -2, okay? And sometimes what I like to do is I like to kind of think about this in terms of a timeline. All right, you think about this in terms of a timeline. The function started at the beginning of the function, at the beginning of time, at negative infinity. The function started off increasing. And so as we kind of look at this thing, break it down this way. Let me draw a little timeline down here. So here's the timeline of the function. And the timeline always starts at negative infinity and ends at positive infinity. And just think about this function in terms of the timeline. As I go from negative infinity, as I follow the timeline of the function is going up. We're in that purple section. And the function continues to go up until I get to this spot on the timeline, which is at -2. And then the function goes down until I get to this spot on the timeline, which is +3. And then the function is going up again as I continue to go to the right. And so as I continue the timeline, the function is now going up for the rest of the function's life, for the foreseeable future here, so positive infinity. And so as I think about that in terms of a label, it was increasing from negative infinity to -2. Again, I label it in terms of x, and I'd use a parenthesis here because I can never actually equal that. The -2 is maybe up for debate here. And as you look at this, well, -2, when you think about it, that's actually a relative maximum. And when we're at the maximum, is the function going up or down? That's the question. And the answer is it's doing neither of those things, okay? That's the moment where it's not going up or down. It's the moment where it was going up, but now it's going down. It's that moment in between. And so we're going to put a parenthesis here because we say, hey, you know what? It's not actually increasing at -2. That's when it stopped increasing, but we don't include that. Okay? See, that -2 is where it stopped increasing and started decreasing. That's the relative maximum. And though the other place that it's increasing was from 3 to positive infinity. And once again, it's the same kind of deal, parentheses all around, and then that union symbol, okay? But now decreasing, it was decreasing from -2 to positive 3. And again, parentheses for each of those because those values aren't included in the increasing or decreasing. They're the relative maximums and minimums, okay? And so when you fill this out, if you're really struggling with this, fill it out like a timeline. Say, hey, from here to here, the function was going up. So I'd go negative infinity to -2, and I put it in the increasing section. And then just do the next section, -2 to 3. It was going down, so then you list that in the decreasing section. And then from -3 to positive infinity, it's going up again, so then I list that in the increasing section, and then go back through and fill in your union symbols if you have to, okay? But again, we identify increasing and decreasing in terms of y, but we label it in terms of x, and I think that's where students really struggle with this, okay? Relative maximum, we're just looking for kind of high spots. They're pretty easy to identify, and we can see there was one right here. That's where the function changed from increasing to decreasing, and so that's a relative maximum, and that's an ordered pair. That's a point that I'm referencing. That's the ordered pair -2, 4. And here's that situation where I see a lot of things that look like ordered pairs, but please understand that this one is an ordered pair because of the context, because a relative maximum is a point, okay? But this is interval notation because I'm talking about an interval on which this thing was decreasing, okay? A section of space where it was going down, okay? And then a relative minimum. This thing changes directions over here. It was going down, and now it's going up. And this is the point right here. At 3, -2, that's the point where it went from going down to going up. So that's a relative minimum. And one of the things I really like about this example in terms of relative maximums and minimums, when you think about it, there are bigger points. Like when I look at that relative maximum, there are bigger points on this function. Like right here. This point right here, that point is higher than the relative maximum that I identified, okay? There are bigger values on this graph. There are maximums above that relative, okay? But that point is bigger than all the points around it. If I only looked at the points on either side, that one's the highest, okay? It's a maximum relative to the points on either side, okay? And the minimum, same kind of thing. There are smaller values, like right here. That's a smaller value on this graph, okay? That is a value below that relative minimum. But this one is the smallest compared to the points around it. It's relatively a relative minimum, okay? All right, end behavior on this one. We're going to keep this pretty basic, but when you think about end behavior is what the function is doing as x goes to plus or minus infinity. Again, that's just saying, hey, what's the function doing at the left side and the right side, all right? X going to negative infinity is the left side of the graph, and x going to positive infinity is the right side of the graph. So when I come up here, I just look at the left and the right. I say, hey, on the left, well, that's what the end of the function's doing. It's going down, right? And on the right, hey, that's what the function's doing. It's going up, okay? And we're always going to list this left to right, and we're just going to list it as up or down. I'm describing the y values here. So for the end behavior, I'm just going to list it as down, because it was going down on the left side, up, okay? So down, up, referring to the left and the right side. So on the left, it's going down. On the right, it's going up. So as I go from left to right, the function goes from down to up, okay? If I look at this next one, same kind of thing. If I just kind of follow along this function, I can see that it's going up, left to right, and then it's going down, and then it's going up again, and then it's going down again, okay? So as I kind of trace this function and just look at it in terms of increasing, decreasing, I can see that it's increasing here. And again, I look at it visually in terms of increasing, decreasing. I'm looking for y. But let's label in terms of x. Again, think about the number line if you have to. Negative infinity to positive infinity, that's the life of the function. Let's see, it was going up until I got to here. So negative infinity to -2 was increasing. And then from -2 until I got to here, until +1, well, there the function was going down. It was decreasing. So that would be in the decreasing section. Doing the other version this time. And then from 1, it started going up again until I got to here, which is a positive 4. So from 1 to 4, it was going up again, so that's increasing. And then after 4, it was going down, and it keeps going down for the rest of this thing. So from 4 on up, from 4 to infinity, the function is going down again. Okay? And then I slap my union symbols in between. So I think about it in terms of the life of the function. From negative infinity to positive infinity, what's the function doing? Where's it going up? Where's it going down? I'm labeling the where. That's why I'm labeling in terms of x, okay? Where is it doing this? Visually, I can see what it's doing based on y, okay? But I label it in terms of x. Where is that happening, okay? And then relative maximums. There's actually 2 of them. There's a relative maximum right here at negative 2, 3. And there's another relative maximum right here at 1, 2, 3, 4, 4, it looks like. And it's okay to have more than one relative maximum, all right? Because again, it's relative to the points around it. And then relative minimum, there's one of those right here. That's at 1, 0. So next, the end behavior here, again, we always just go left to right when we state the end behavior. So I look at the left side, and then I look at the right side. And, the thing about end behavior is, we're describing it left to right, but we're looking at it in terms of whether the function is going up or down, all right? And I think that's the thing that confuses students sometimes. But, again, you look at the left side. The thing is going down, so down. And on the right side, it's also going down, okay? So as I go from left to right on the function, it was starting in the downward position and it's ending in the downward position, okay? We're describing each end of the function, okay? All right, the last thing we're going to look at here is finding the end behavior, but this time we're going to find it from an equation, all right? So we've looked at all the different components of the graph and kind of how the graphs of these things work and how they function a little bit, the different things that we're looking for. But now we're going to start going from the equation and be able to graph these things, okay? So from the equation, I want to find these different components, these different pieces, and then I'll be able to draw a graph. And the first component we're going to find here today is just finding the end behavior based on the function itself, based on the equation, all right? And simple memorization here, and we kind of already have this memorized if you think about it, but if we have an even degree polynomial, we look at the leading coefficient. If the leading coefficient is positive, then both ends open up. And if we have an even degree polynomial and the leading coefficient is negative, well, then both ends open down. All right, and so when I'm talking about positive or negative, I'm talking about the leading coefficient for each of these, okay? Same thing with the odd degrees. I'm talking about the leading coefficient, but we kind of already know this. Think back to quadratics. If you think about a quadratic function, remember a quadratic, that's an even polynomial. It's an even degree polynomial. It's an x squared polynomial, all right? And if I have a positive a value, like a 2 out here, well, then I know that this polynomial, that this quadratic opens up, which means both ends open up. It's up, up. And if I think about changing that value, if I were to change this and say, hey, you know what? Let me give you a quadratic, like a negative 2x squared. Well, one of the things we know right away about that is because the leading coefficient is negative, the parabola opens down. All right? So this is an even degree polynomial with a negative leading coefficient. Both ends open down, so it's down, down. Every other even polynomial is going to do the exact same thing. So if I did the same thing with like an x to the 4th function, if I change that to a 4, well, if it's an x to the 4th and it's got a negative leading coefficient, both ends are going to open down. And if I change the leading coefficient on an x to the 4th function to a positive, well, now both ends are going to open up, okay? So think about the quadratic. Think about the even degree polynomial we already know how to deal with. Every other even degree is going to do the same thing, all right, in terms of opening up versus opening down, okay? So when the leading coefficient is positive, both ends open up, all right? And when the leading coefficient is negative, both ends open down. And then the odd degree, you might not recognize that you've seen an odd degree polynomial before, but you have. It's the first degree polynomials, okay? And so if I looked at something like this, y equals x, all right, think about the graph of y equals x. Yes, this is a polynomial function. We don't think of it as a polynomial function. But if you thought about this guy on a graph, positive slope goes like this. Look at the end behavior. On the left side, it goes down, and on the right side, it goes up, okay? And so if I were to change the leading coefficient, if I made it like a positive 2, it's the same thing, right? Up 2 over 1, up 2 over 1. On the left side, it goes down. On the right side, it goes up. But if I changed it to a negative, let's change this thing to a negative. If I did like a negative 3, that would be like down 3 over 1, down 3 over 1. Look at the end behavior. On the left side, it goes up. And on the right side, it goes down. And so we're doing the same thing. We've always looked at the leading coefficient as slope. Well, think about it the same way in terms of identifying your end behavior. And so when we look at something like this guy, our classic example of an odd degree polynomial is a line. And think about it. When a line has a positive leading coefficient, when it has a positive slope, it starts in the downward direction and heads towards the upwards direction, okay? It's down, up. And when the slope, the leading coefficient, is negative, it starts in the upward direction and goes towards the downward direction. And so we apply that same thing to all other odd degree polynomials. So if I had y equals, a 5x to the 11th, well, this would do the same thing because it's an odd exponent, but it's a positive coefficient. This one's going to start in the downward direction and end in the upward direction. It's going to follow the same thing as positive slope. And if I change this to a negative 5, well, now it's going to follow the same thing as negative slope. It's going to start up high, so it's going to start in the upward direction. So on the left, it's going to go up, and on the right, it's going to go down, okay? And so again, think about the ones we already know. Every other function will follow that same pattern, okay? For example, if I look at something like this guy, it's an odd degree. So because this is odd, that's a 9, all right? It's going to follow like the slope of a line. So just think, the slope of a positive line goes like this. The slope of a negative line goes like this. And since this has a negative leading coefficient, this one's not going to be a line, but it's going to follow the same pattern for end behavior. Because it's a negative coefficient, it's going to follow the same pattern as a negative a line with a negative slope. On the left side, it's going to be up, and on the right side, it's going to be down. So my end behavior for this one is up, down. Okay? And again, I always list left to right. If I look at the next one, I look at the degree, and I say, hey, this one has a degree of 2. Okay? So it's an even degree, so that means either both ends are going to open up or both ends are going to open down. Well, it's got a negative coefficient, right? So because it's even, it's got a negative coefficient, that means the thing opens down just like our parabola. This one actually is a parabola. This is a parabola that opens down. Well, look at the end behavior. Both ends open down, so the end behavior is down, down. Okay? And again, I'm just describing left to right. If I look at the next one, the next one's a little bit tricky only because it's not written in the right format. Remember, these should be written in standard form, so in descending order. So it should be written as 8x to the 4th minus 3x squared plus 1. And now I look at the degree. The degree of this one is right here. It's a 4. It's the biggest exponent. And so this is an even degree. And this one's not a parabola, but it's going to follow the same pattern as a parabola. If I had a parabola with a leading coefficient of positive 8, well, that parabola would open up, which means each end would open up. And so if the parabola had a leading coefficient of positive 8, it would be up, up. Any polynomial with an even degree is going to follow that same pattern. So even degree polynomial, leading coefficient is positive. So this one, both ends are going to open up. So up, up for my end behavior. Okay? If I look at the next one, again, this one has a degree of 3, so it's an odd degree. There's a negative coefficient, so I follow the pattern of a negative line, right? If you think about a negative sloped line, it goes up, down. Every other odd degree polynomial is going to follow that same pattern for end behavior, okay? So this one is up, down. And then this last one here, this one's a little bit tricky because it's also not written in the right format. But writing in the right format's not just a matter of moving things around. I would actually have to multiply this whole thing out in order to put it in the right format, and that's a real pain. okay? But here's the thing. When you think about what I looked at in each of these functions, like in this function, I only looked at the first term. In this one, I only looked at the first term. In this one, only the first term. In this one, only the first term. So when I think about multiplying this out, I only want the first term. And so if you kind of think about this, let me write all of this out as if I'm going to multiply it. And we've done some pretty hefty multiplication, especially with binomials, but this one would be a real pain, okay? If I wanted to actually multiply this out, you see I would have to do my distributive property here and get a trinomial, and then I'd have to do my distributive property with this guy and the trinomial, and then I have to do the distributive property with the next guy. Let's just think about this for a moment. I only want the first term. And if I only want the first term, I only need to multiply out the first terms of each. See, I don't care about the rest of this function. I don't care about the rest of the values within this thing. I only care about the first term. And so if I only multiply out the first terms, it gives me a negative x squared times x. I've got 1, 2, 3, 4, 5 of those x's. This is going to be x to the 7th power. Okay? So if I have a negative x to the 7th power, well, that's now an odd exponent. And if I multiplied out this whole thing, I'd have a bunch of other terms here. I'd have an x to the 6th term and a 5th term. But again, I don't care about any of those terms. I only wanted the first term, so I only multiplied out the first terms. Okay? That's what the kind of shortcut we need to take on this thing, because it would be a pain to multiply this out. Okay? And so as I look at this thing, that's a coefficient of -1. So an odd exponent coefficient of -1, that's going to follow like a negative slope, and that's going to be up, down, okay? If it was an odd exponent with a positive slope, it would be down, up, all right? So just think about it, all right? Think about it compared to your original, to the one function that you know how it works, okay? And so even exponents, they do the same thing that all parabolas do. When it's positive, both ends go up, and when it's negative, both ends go down, okay? Odd exponents do the same thing that a line would do. When it's positive, it goes down to up. When it's negative, it goes up to down.